This isn't on, is it? Yeah, so much failure. Danger, Will Robinson. Yeah? You like, yeah? Gotta use the danger, Will Robinson. It's great. Justifies. Okay. Okay, so good. So we have, so complex networks, this is going to take up about 4 or 5 lectures, 6 lectures, lots of stuff. So we can kind of cruise into this a little bit. Problem set slow down a little bit. So your problem set can be due tomorrow. I mean, it is due tomorrow now. We could make it due next week. Look at you guys. This is Tuesday. Would that be better? All right, let's make it Tuesday. All right, okay. Next problem sets are a little bit smaller and, yeah, okay. Well, I can make them as small. Yeah, so that complicates that. So it may get pushed a little bit. Okay. Right. Yeah. Is that good?
Yes.
No?
Yes.
I know you've been suffering. Which is the appropriate thing to do. I want to say that. I've started a blog, actually. This is just a tiny thing, but I used to have a blog, and it was basically like, it was Twitter. I mean, in a sense, it was Twitter. It's like, here's an interesting thing. Twitter is perfect for that. But so that's my first post. Speak Phil, right? It's how words taste. So there are lots of good words. Plinth, pickle, dork, spork, and pork. These are just good words to say. And that's the little joke about that. And they're words you say until the meaning goes away. It comes back when you stop saying them. All right, what else? Okay, so let's start on this. This is good. All right. So now we get into, this real framework that emerged at the end of the 90s for complex systems. And before that, it was a little bit mushier. You know, we've talked about what complex, they're real things. They're everywhere, right? And it is where the science had to go eventually, but it wasn't that concrete, right? It wasn't solid enough. So sometimes the field would get knocked for that. Although, of course, people miss the fact that fluid mechanics was this incredible success in complex systems. All right. Okay. So there are 2 main sets of slides. The first one is going to be just an overview. And so I'll give you, some examples. You'll understand. I mean, these things are all straightforward. But I'll sort of give you a sort of a taxonomy there. And then some basic properties, right? So this is an important thing. So this has been somewhat hard fought for. We're talking about real networks, ones that actually matter and exist, ones that are inside you, right? We have blood networks and neural networks and all sorts of things we're running around in that we depend on. We have transportation networks, we have power grid networks, we have supply of water, supply of Coca-Cola, right? All these sorts of things. FedEx and UPS sends the little boxes from Amazon to people. So there are all these kinds of dynamic and real fixed sorts of networks. So they're ubiquitous, they're such a big deal. But the properties of them, that's taken, the last 15 years we've been sort of sorting that out. And I'll mention graph theory. Of course, graph theory has been around for a long time, so you'd think that would be all nailed. But the issue is that graph theory is part of math, and math is not really about how things become things necessarily. I mean, it's in there, but physicists and everyone else are obsessed with becoming. So how do things become things? And so as soon as you ask that question, you focus on that. How do these networks emerge? Then you start to measure slightly different things. So we'll see that this is still a bit of a grab bag of elements, right? We want to measure this part of the network or this aspect of the network and another aspect. It's not like we have something like a Fourier decomposition. So there are some areas where you know how to break it down to little pieces in a really clean kind of way. There are lots of examples of that. Wavelets maybe for images and so on. We know how to sort of break it into pieces. That's harder. So you'll see we kind of move our way out slowly. All right, so I like words, as you can see. All right, so let's think about where network comes from. And this is a very odd connection to my distant past. So network, right? So there's a history in talking about physical things, roads and railroads, and then transportation. And I have it, I guess, on, this is just straight from, you know, the Mac thing, but I'll give you some etymology. But then it gets to people, right? So we start to get to people and computers, so it becomes more and more abstract in meaning. We realize, well, this is another network. It's all to do with spiders, though. Okay, all right. And of course, there's the verb to network. But there are lots. It was a very nice word, delicious word. Okay, lattice, net, matrix. We ended up with web, World Wide Web. That really stuck. As people from Pittsburgh say, the W. So I have relatives. So let's see. So these are all pretty kind of interesting words. Reticulum, we're getting a little bit of sort of Latin going on there. Labyrinth, fantastic, all right? So, and that's complicated, complex. Yeah, all right, that's not good. So Keith Briggs was I think a PhD student when I was at Melbourne as an undergrad, and he was trying to figure out, as I recall, the Feigenbaum constant. If any of you have taken chaos, there's this weird thing, the Feigenbaum constant. And just like pi and e and these other numbers, there's someone somewhere trying to find the bazillionth digit of it. And there's another person who's trying to remember the first million, because that's fun. They're unemployable, but you know, you can use them for charity or something like that. So, you know, humans. Yeah, that was what he was working on. But so he works for British Telecom, I think now. Anyway, so he has a nice little piece on the web, at least at some point. And there's an old origin of the word. So opus reticulatum. So this is network. So this is, you know, a work in the form of a net. So here it's construction, right? Build a wall built like a net. So that's one piece. There's the word network appearing with an E, of course. You've got to put an E on everything when we go back in time. So maybe back in a version of the Bible in 1560. And this, so this is actually a very physical thing. So a little bit of a history again. So I mentioned this kind of evolution of things. This is actually biological to start with, I guess. So, you know, people doing bad things to animals and looking at what's inside them. And getting in trouble if they get caught, especially when they start to look at people. You know, you had to do that in secrecy. Rivers and canals, right? So this is very important. This is how things were connected and stuff was being moved around. So this is like FedEx, but a long time ago. Railways, that appears, and that's a big deal. I guess the telegraph would have been in here too. So, you know, the telegraph is the big switch in terms of information spreading around, because suddenly you've got instantaneous delivery of information. It's a big change. You know, you could know what the weather was like somewhere, or how the crops were going. You know, if they all failed this morning because of a frost in some other province or something. Information was being spread very quickly. And of course, they charged in such a way that that putting in code and abbreviating things was important. It's just a very natural thing to do. And some of the companies would actually try to stop you from using certain code because you were being too smart. You know, you were cheap, right? But it was Twitter. I mean, it's basically, you know, LOL. They were using those kinds of things that have happened on Twitter because that's 140 characters. All right. Okay, so electrical cables start, and then we have wireless broadcasting. So we talk about networks there. So it's lifting and lifting and lifting out of physical and biological into more abstract worlds. Okay, more fun things, right? So net has a nice origin. It's spiderwebs. So there you go. Right. You know, and people go back, and OED loves to try to find the first appearance of things. So this is 888. And work is just used then in this, you know, so you have ironwork or lattice work or these sorts of things, stonework, fretwork. So it's a construction in the nature of a web. So good, spiders. All right, all right, so there you go, little etymology. So complex, so the big observation, it took a long time, and people probably said it in all sorts of ways. You can find it's written down in the 1940s and 50s and 60s by all sorts of people in different fields, saying networks are interesting, but they didn't have a solid data really. You know, there was some, but nothing big. And so we get this transition, as I said, around the end of the 90s, and I'll show you that it's been quite popular, let's say, scientifically, and in the main press as well. So lots of systems actually really are networks. You can think of them as networks. There's lots of interactions, social networks, of course. The power grid, they're fundamentally networks. In some way, there's some sort of big network structure underneath. They're not just a big mixing soup. If you think about the early models, which we'll get to eventually for biological contagion, for spreading, they were all just random mixing things. And even in 2002 or 3, modeling SARS, for example, paper that appeared in Science magazine, where nothing bad ever appeared. Yeah, lots of, it's Nature and Science, there's a lot of controversial articles, but this one used a model that was basically just a big mixing model, right? It's mathematically kind of okay, but that's not a very good model to use for Hong Kong or for the world. It doesn't work like that, right? But the problem is it's hard. It's much easier to make a mixing model that says everyone talks to everyone. Okay, but so once we got to networks and certain kinds of networks, that's really what it was, that were tractable. Mathematicians had studied purely random networks for a long time, and we'll talk about those, purely random networks, but the world has none of those, 0. Although if you have a box of networks, created by a mathematician, if you like, and you reach in, the one you find will never exist in the real world. All right, we'll get to that later on. But it did open, so it was kind of an observation of real world stuff, opens it up all this kind of mathematical techniques and of course numerical stuff, but lots of analysis, which you'll do a tiny bit of, not too bad. So the people who took off here were these theoretical physics characters, right? They're like, oh, I didn't go to Wall Street and I have all these things in my head and I need something else to, dine on, so they got excited. And there's been a crazy amount of work since the first big papers, well, what are now seen as the big papers, came out in 1998. There are some precursors, as we talked about this with Stigler's law, and there's usually someone who's done something before, but things really do take off in 98. So your typical theoretical physicist is one of these characters. They tend to hunt in packs because they're really social creatures, and they just destroy things that appear. Whole fields get eaten by them. They just chomp their way through it and then move on to the next one. It's like the little kids playing a soccer game, right? The ball squirts out and then or piranhas. Okay, so I'm associated with these humans a little bit, but so I can say that. All right, let's see. So these are the two big papers, and they're still big pieces, right? They're still big pieces, and we'll go through these in depth. And I've in particular done a lot of work in the past that's associated with this one. I mean, and I worked with this character, Duncan Watts, at Columbia for many years. So we'll talk about that. But these are two distinct groups, and they're two very distinct problems, as we'll see. This is something to do with these small world networks, which we'll get to. It's 6 degrees of separation, the idea that Kevin Bacon is close to everyone in the movie actor graph, which is, fun and probably annoying for him. But in math, there's Edish, and we'll come to that. That's people talk about their Edish number, how far away they are in the publication record, right? So Edish has a number. His Edish number is 0 because he was himself. And if you published a paper with him, you have a number 1. If you published a paper with someone who published a paper with him, you have a number 2, an Edish number 2. And so it's the same idea for movies. So we'll get to that, and then you can have an Edish-Bacon number, which means it's not infinite. Okay, so we'll get to that. You've been in a movie and you published a paper that's, which is fun. All right, so we'll get to that. But this turns out to be a simple property of many, many networks that gives rise to all sorts of things. That spreading is facilitated, that search is facilitated. Lots of interesting aspects about this pretty general property of networks, which no one had ever really elucidated. Okay. So that's one thing. And then we'll get to this, emergence of scaling. We've got some more of the scaling business. So we had the parallel size distribution thing. That's going to come back. The rich gets richer story will come back and reinvent itself. I've mentioned this paper before, Barbazi and Albert. Here's the title, and we talked about preferential attachment. So this is about networks growing, emerging from nothing. So very much in the same vein as the Simon model, but independently constructed, right? So this one has 23,000 citations and 20 here. So that's pretty good, right? So that's more citations than almost, 99.9% of scientists will have in their careers. Yeah, famously, I guess famously within academia, no one else knows this, I suppose, but the mode number of citations for papers is either 0 or 1, right? So because it's one of these heavy tail distributions. Most papers get, so on Google Scholar, if your paper has 10 or more citations, that's kind of included as a thing. Like that's well done. If you get to 10 for your paper, they'll put a, you get a little mark somewhere, right? And like, good, yeah. There are other metrics, but that's a very basic one. So it sort of exists on the scoreboard. Okay, yep. So this, these are huge. And this is just gigantic. And I update these every year, and they add 2,000 to 3,000 citations. So of course, what's happening is, and if you think about this a little bit, it should make sense. Many of these citations are networks are interesting. Citations 1 through 12. Blah, 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 blah. Now I'm going to do my thing. So that happens. These are talismanic, touchstone kind of pieces. There's been a ton of work done on both of these areas specifically, but then you also get, you're getting, well, even hundreds of citations, but certainly when you're getting tens of thousands of citations, it's in that kind of, you've got many of them that are like this. Networks are interesting, 1 through 27. Pretty fun. All right, so we'll get to that. There are a couple other big pieces around. You may want to sort of read some of these, I suppose. These are a little more, they're mathematical. They're mathematical. So Mark Newman will talk about his work. We certainly talk about a lot in complex networks. These are review pieces, so they're summary projects where you come along at some time and say, okay, here's what we know, and these are going forward in time. And I should look to see if there's a new review of these. I'll show you some books. There are many books around about this. I mean, networks has become a mature field. So-called complex networks have become a mature field. So we've probably moved through many of these things. But you can see these are doing well for themselves as well. So there's another one with Reka and Barabazi. Yeah, that's not bad. So it's a big deal. It's a big deal. There are a couple of textbooks which have different flavors to them. Mark Newman, who is ridiculously prolific, who's at Michigan now, who's at SFI, Santa Fe Institute for a long time. Networks and Introduction, probably more than an introduction, solid. And so John Kleinberg, so I did not know Easley, but John Kleinberg's they're both at Cornell, so Easley's in economics, Kleinberg is in computer science. Some of you may have heard of him. So he's a MacArthur genius. He both is a MacArthur genius type person, and he got one. So he's that sort of character. And he works with Strogatz as well, so all these people are connected. Right. So that's an interesting piece, and it brings in some economics in there. So yeah, there's that. Some other things. These are just some of the early popular pieces, right? So these two books are popular ones, right? We'll talk about this later on, why this whole match thing is just a really bad story. When we get to social contagion and spreading and contagious stories. Yeah, Gladwell is frustrating. But actually right now he's come out and said he's a storyteller. He just tells stories. He's not, he has some line, he talks to scientists who are not very good at explaining what they do, and then he tells stories. But of course it all comes across as universal truths that are used by governments and corporations and so on. I mean, you just hear it all the time. Just the Board of Trustees meeting last year, one of the trustees piped up with the David and Goliath book, which is just popular. I'm like, no, don't say anything from Gladwell. He's crazy. Good hair, he does have good hair. Okay, so, yeah, so we'll, of course, it's a mixture of things that are great and then some stuff that's a little, Mark Buchanan is a pretty serious science writer, and so he got into this early on. He has a sort of a string of books like this. He has another one which is about why things explode, which is basically about parallel size distributions, the whole business. Yeah. They're popular ones. So they're from journalist characters. These are, so here are our characters again. So this is Duncan. So he spent a lot of time in New York City in coffee shops writing this one. And Barabazi. So they produce their books, so they have their big works and they're getting a lot of success. It's the Matthew effect, the rich gets richer thing, and which everyone is aware of, and including very much these guys. It's fine, it's just the way it works. And so they produce these popular books. They're very, they sell very well. So these are again early on. So maybe this is 2005 or 6. Lots of other books, and I can point you to more beyond this, but some of these are then, these are mathematical ones, so physics, mathematics. This has, to do with my past, right? So river basins. This is from an economist, a Spanish economist. Then there are more this is from sociology. This is a handbook that's been around for a long time, kind of a venerable piece. This is very strong math business. Okay, and then these kinds of handbooks. So there are lots of other books like this, all right? Good. So it's a big field. It really exists. It really matters. We're helping the NSA, I suppose. Complicated business. All right. So networks aren't new, and we've known about them. Obviously, we've had graph theory for a long time. Something to do with Euler wandering around Königsberg, thinking about bridges and, being very, very smart. That seemed to be, people often pin that as the start of graph theory. If you look at the study of social networks, that's the 1930s, and it starts to take off. Of course, it's field research. I mean, it's a venerable part of the scientific enterprise. You go and ask people who they're friends with, and et cetera, and you start to create what were called sociograms, I think was sort of the term. But pictures, look at them, look at the average number of friends people have, or who has the most friends, who's important. There are lots of framings of this, talk about connectors and influentials, and we'll get to that later on. Bridges, this sort of thing. All right, so why do we have all this new stuff going on? Well, it's, as I said, data. Data just emerges, and it goes boom, about people in particular. And unfortunately, our theories are in trouble, right? We have to look at reality a little bit. So that usually is a bad plan if you really like your theory. Really should not do that. Okay. But this is exactly how, without data, things just, theory blossoms, right? And of course, we've talked about this, especially with, say, the rich gets richer thing, which we'll reprise again. But in general, you need a mechanistic explanation. And we've seen the trouble we can get into now when we try to understand much more complicated things. The eureka story, right, is disconcerting, right? We might not be able to do this for much longer. Our brains are too small. String theory is good. You might want to stick with the physicists here. You might want to really stick with the string theory, because reality is, obviously it's relevant, but no one's going to measure a string, right? So it's very, very smart. Okay. It's provably untestable, which is great. So let's see. So, all right, a little bit more about data. I know I've talked about data a lot. It's just such a huge deal. I have this extra slide here. People have gotten a little carried away with this story, though, right? So here's a piece that appeared in Wired. The end of theory. It's all over. No more, right? The data deluge makes the scientific theory obsolete. Like, done. Don't do it. Stop doing it. Just count things. Just count all the things. And there's another piece. These are some Google characters. The unreasonable effectiveness of data, which is a kind of a funny way of saying that looking at reality matters, and there are many of these, the unreasonable effectiveness, because it's a play on Wigner's sort of very famous piece here, the unreasonable effectiveness of mathematics and natural science, which is a philosophical piece of like why do equations work? Oh my God. You can be a physicist and you're describing all these things, and you're writing papers, it's great, and then one day you have this existential crisis, like why do numbers work, and it's a bit like that. So this is madness, right? This is madness. This is fine for Google and Amazon and so on. They don't need to understand why people buy the badonkadonk tank and this thing, right? They don't need to know why those people associate those things together. They just need to tell you that that's what they do. And then it reinforces itself and more people buy these guys, right? People are generally happy with that. I'll talk about Walmart very briefly later on, but Walmart, years ago, I think it was Hurricane Ivan, perhaps. I mean, one of these bad things, was coming. And they'd learned from the previous one, or maybe they'd learned from Ivan, that they have all this data, right? They have tons of data. And 4 or 5 years ago, the amount for them was a petabyte, and now it must be incredible. They're employing data scientists, right? So Target just scooped up a climate science guy that we know who's a postdoc, straight to Target, right? You could go to Wall Street. Now you can go to these big organizations. Anyway, so one of their stories was, you think you might put more, I don't know, shovels and sandbags, something, right? But they look at, you have this thing popping out that, I shouldn't say popping, the thing that You look at what people did around the last hurricane, what they bought beforehand. I mean, you just look, right? You look at the numbers, and of course you do it by zip code and all sorts of stuff. So it's Pop-Tarts, right? So it turns out people buy Pop-Tarts disproportionately. So they're like, sure, we're going to give you more Pop-Tarts. So they truck the Pop-Tarts in. Yeah, because an algorithm, which is putting beans in boxes, says more Pop-Tarts. Presumably some other things, you know, but like water. But yeah, anyway. So, but they don't need a theory for that. They don't need a Pop-Tart theory. They don't care, right? I mean, they don't need to care, yeah. So we need to understand, of course, we want to understand because we're pretending to be scientists still, so it is hard. All right, so you can get a little carried away, but we definitely are in this realm now of you've got to describe things well. You've got to do a really good job with that, and it's quite hard. So there's a lot of data wrangling to get through before you can say, okay, now I think maybe I can understand. All right, so we're going to have some very basic definitions, and then I'm going to talk about some examples and some properties of complex networks. I want to lay out this kind of very peculiar kind of taxonomy of things that seem to be important about networks. Real networks, real ones. Okay, so, right, nodes. We'll talk about nodes in general. So these are just entities that are connected in some way. So they could be a fork in a river. People, obviously, protein interactions, gene-protein interactions, web pages, organisms that eat each other, or whatever it is with the ecosystem thing. So there are elements. It's often much better to think about the links. Actually, analytically, we kind of want to think about the nodes because of our whole narrative thing. We're humans, we want to be the individuals. But it's the links that are much better to think about, probably in a lot of circumstances, but certainly analytically, it turns out to be the way to do it. So for disease spreading, for example, instead of thinking of one person as being a big deal, you want to think of the connection that they make or may make as being the thing to think about. Like, how many new outgoing connections does that create? That's really so an infected link begets how many infected links? It's about, you think about it in link space, it's better. Okay, so links. So we'll call them links, and they can be directed or undirected and binary and weighted. These are very basic things, right? Could be just a link or no link between nodes. It turns out that going to weighted links, which you think is, you've got to do that. I mean, obviously we do it in circuits, electrical circuits, for example, that we've constructed them. It's fundamental to it. But understanding a lot of these networks that we've started to get data for, people just sort of put in, there's a link between them, And that was hard enough to just deal with that. So like the actor graph, for example. So two people act in the same film, you just put a link between them, which is pretty soft, right? But that turned out to give you an interesting enough network to be able to just contend with that. So a lot of theory was developed for binary links, just ones and zeros. Okay, and mathematicians would call them maybe vertices and edges. So here's a big deal. This took a long time. This took 40 or 50 years, really, for people to kind of say, oh, that matters. I mean, we knew about it, but obviously it's fundamental to networks, but degree, right? So just the number of links per node. Just how much this matters overall. So really, think about the distribution of it. What's the distribution of this thing? And then there's how everything's connected, but what's the distribution of degree? That was, until 1999, no one had ever really said, this is what it's all about. Okay, we'll come back to that a lot. So simple thing, what you usually see in the literature is K sub I, so node I has degree K, that's how many friends it is. So you can see immediately how much more complicated this will be if it's weighted, because you say I have K friends, this friend is, whatever it is. We could be talking about octopuses eating each other or something, but it's the, or a platypus friendship thing. So, the strength of the link matters. So that's a lot more information. But much easier to say, well, they just have 5 friends. All right, so they can have 0, 1, 2. And we talk about the average degree, and I'll use this notation generally, right? Bra and Ket. Sometimes in the literature, for some reason, you see a Z or a Z. Okay, there, sometimes Z. All right, so simple thing, the number of edges in a network and its average degree. Right, so you've got some network, happily being a network. So each edge, if we take this out, it's got 2 ends to it. Simple thing, has 2 ends, right? So 2 times the number of edges give you the number of links coming out of nodes or attached to nodes. So 2 times m divided by the total number of this is the number of nodes, it will be average degree. Too excited. Okay, simple thing, tiny thing. And we can do this. We'll say, that should be a calligraphic n. Which I'll change back, because I know it upsets mathematicians. Okay, so actually when it's calligraphic. Yeah, so you can divide, you have some little thing, gamma sometimes is used, but we've got a gamma function, that's all good. So it's a set of neighbors, right? So that's important. So these are very basic pieces, right? So once we've got this, we've got our network. And an easy way to represent things is in an adjacency matrix. So what's this guy? Not a big deal, I guess, but right. So this says I is connected to j, I is the row. So if you go down here, 1 to 5, right? So this is node 1. Node 1 is connected to 2, 3, and 4. So you can think about how you'd store this in a computer. It's fine. You can just put this big adjacency matrix like this. But if it's a giant network, then you're going to have a sparse one and deal a little bit. If it's dynamic, you have to cope with that a little bit, right? If you're adding and subtracting things, if you're evolving the network, you have to be a little clever. So 2 is connected to 3 and 5, and these are directed. 2 is connected to 3, and a 5 out here. So if it's an undirected one, it depends analytically, but an undirected one you represent it with a symmetric matrix. 3 is connected back to 1. 4 is connected to 2 and 5. Did I get that right? So there's a link back this way. 4 is connected to 2 and 5. And 5 is, this is a mess. 5 is connected to 2 and 4. Yeah. So there's a link back this way and a link back this way. Maybe I got that right. Okay. So numerical work, yes. You're going to use sparse matrices. And there's an aspect, I guess I'll say it on the next couple of slides. The reason you can do this is because most complex networks are actually sparse, right? These big, giant networks are sparse. So that's a feature of them. So that's this slide. So what are we talking about when we talk about complex networks? Well, they're usually large. Large being, I'm going to leave that pretty vague, but they're big. They're sparse, so it's a low edge to node ratio. And you can certainly say all sorts of things about, rather fully, nearly fully connected networks, but we're not going to have those. So you think about the whole world, you think about people's connections to each other, how many good friends do you have? My 9-year-old daughter at some point had 10 best friends, which was interesting. But you can think about how many, good friends of a certain level that you have, and then people, that's obviously a very sparse network. Given there were, what was it, 7 billion people? You probably don't know all of them very well. That's sparse. If you relax that a little bit and say that one person would be able to recognize the face of someone else, just that, then suddenly everyone points to Obama and Oprah, the Queen of England, right? You'll be able to recognize them. I guess not everyone in the US can recognize who's the president. Yeah, anyway, so, which is interesting. Anyway, so let's see, what else is there? Yeah, so that's, you loosen that thing. But most, even then it's sparse. Even then it's quite sparse. There's usually a dynamic evolving aspect to these things. There's usually something dynamic going on top of them. But that, as I was saying, this took a long time. It took a long time to just understand structural features of what we're calling complex networks, just the raw structural features, how they're connected together. We got somewhere early on with dynamics, and so dynamics of the networks and dynamics on top of them, and then both of those things together. And more recently, there's been work on coupled networks. 15 years, long time. And an unreal number of papers. All right. Lots of things, and I'll give you a little taxonomy now, but social, economic, natural, all sorts of things. Okay, so that's where we are. I'll give you a few examples. This is a very broad taxonomy. River networks, obviously I'm a fan of these things, but that's the big network structure on the surface of the Earth. Neural networks, so these are physical ones. I mean, they can evolve and change. but they have a physical stability to them. Trees and leaves, very interesting. Trees, of course, go from a three-dimensional, a thing that's filling three-dimensional space to a two-dimensional network that's filling 2 dimensions. So there are all sorts of interesting, people are still figuring things out about these, which is pretty cool, right? I mean, we're getting better and better. A lot of this is about remote sensing, right? So you put your leaf in there and you take a photo of it in some way and extract the leaf network in an automatic way, then you can build up your data sets. Trees are actually kind of hard, right? You want little tree butts this is actually an old idea of us. So you have little things that run around the tree and map out its whole shape, and then you have it actually physically, you'd be able to put it in a computer, but we don't have that. Blood networks, which has been mapped out because again, painstaking for the person doing it and the individual being mapped, which has often been rats. And this is, in the literature, you'll see cat and dog and so on, and of course a few people who have donated themselves. So these have been mapped out in certain ways. That'll get better and better with sensing. So this is this is an enormous deal, right? I mean, how well is this structured in someone? How is it evolving? Angiogenesis is the growth of the blood network. Resilience and all sorts of things in there. One more thing I want to say, circle of Willis, right? So you have 4 delivery systems of vessels coming up to a circle in your head, so we have a redundancy. It's not just a pure branching network, because that could lead to being toast, which is true of a tree, right? You take out the trunk and it's all over. It doesn't have more, generally speaking. There are trees with funny roots, I suppose. Yeah, early in Australia, ring barking was the way to get rid of trees, right? Which just means you cut around the tree. It's toast. Get through the xylem, I guess, and it's all over. Very nasty thing to do. But there's a branching ones have this fragility to them. They're good at doing something very well, but they can be broken. The internet, pictures of the internet are hard. But that is a physical network, very different to the web. Road networks, obviously, power grids. And we've talked about this as being an emblematic, complex system that was engineered, but then arose into this higher and higher levels, and much more dangerous things can happen. All right, so for physical networks, you could broadly break them into distribution type ones and redistribution ones. So road networks, there's a lot of local distribution and redistribution, or sort of, you could think around a city, people coming in, people going out, that sort of thing, but broadly speaking, it's a big redistribution structure to allow people to get from one place to another, or little Amazon boxes. What else? Yeah, leaves actually have lots of cycles in them as well, so they're fairly resilient. You can cut out Marcello Magnasco at the Rockefeller. I saw him getting undergrads from Stuyvesant do this. You've got your nice leaf, and you cut out a middle bit of here, just remove it, and it'll be fine, depending on the leaf, but they're fine. They have lots of cycles around them, through them. All right, fine. So that's blah, blah, blah. Okay, the blogosphere, which I guess still exists, but it's been trimmed down a little bit. These are interaction networks, biochemical ones, again, gene, and gene protein, and protein. Food webs, we've talked about them as being a difficult thing to remote sense. Who is eating whom? Go out and interview the organisms. Did something bad just happen? Beepy thing? Exploded? Okay, shrug. Let's see. All right. The World Wide Web, yeah. Airline networks, so they're not physical, right? They're movable and so on, and you can change flight patterns. You can change these are somewhat adaptable objects. Call networks, so that's a famous kind of network that's been studied for a long time. So that's a place where there was data about a social thing. And for some reason, it didn't give rise to the revolution that we saw at the end of the 90s. I don't really know why that is, but people were definitely working on that, helping AT&T do things. What is it? Does AT&T do things well? Did they succeed? I don't know. But that's had a lot of technical people, very brilliant mathematicians working on that over the years. Media. All right, so here's a little example. It's in the middle of this. So this is interactions between, and there are so many I could show you, but I'll just give you a few. So this is a this is a famous paper now, so it's a 2005 or 6. Cesar Hidalgo, who gave a talk here in the Macmillan Symposium that we ran earlier this year. Now he's at the MIT Media Lab, but this is work with Barabasi, this Barabasi character. We'll talk about him a lot. This is so difficult things, networks, and we'll talk about this, to render. And so these aren't all of the interactions, but what's going on here is these products, so it's product space, so these products are connected based on the degree to which, to use that word again, the amount to which countries, individual countries, produce them together, right? So oil doesn't necessarily get produced so much with electronics, right? There are a certain number of countries that just produce oil. So he's done the same thing now for cultural exports. I don't know if any of you saw that talk, but cultural exports, so famous people. So countries start off usually with something like a dictator, that's what they're famous for, and sports people. They've got these famous soccer players and so on that have traveled to Europe. And there's this, and then eventually you start to get artists and scientists, and politicians certainly come early, and directors, that sort of thing. You get storytellers, I think, really, and writers, for example. So storytellers kind of become the emergent cultural production. And the most recent one to add to that list are directors of video games, or whatever the right word, because these are monstrous productions now, not like that Thing in the Spring thing, which was written by one guy in the basement. They're monstrous productions, and they're in front of movies now, I think, right, in terms of gross revenue, I think. Yeah, so that's sort of, it doesn't mean that's the most sophisticated thing your country could produce, but it's kind of, that's, everything else is kind of going well when you can produce some characters who just make up imaginary games for other people to play in. That make them very happy, right? Okay, so this is an interesting study. So it's another network story. The thing that is then, that then comes out of this is you can start to think about countries that are similar to each other, where they've been in the past, where they might go in the future. And then, how do they move around in this space of products, if you like. Right? They may, can you jump from just growing fruit to producing, chips? And there may be some examples that have done that, but there's sort of a history, on average, that suggests it takes a bit longer. You have to move through some stages. Now, that may not be true because you've learned things from other places. Snogging is a nice word. It's okay. Actually, yeah, right. So this is funny. So, it is very funny. So interaction networks, so social networks, obviously the kissing thing. So this is Peter Behrman, who is the head of ISERP at Columbia. I think he's still the head. He did all sorts of things. He's done all sorts of things, interesting things. So one is a study of doormen in New York City, because there's no so the interesting thing to him, I guess, was that many other aspects about doormen, but one is that you never see an advertisement for a job. It's all word of mouth. It's just very interesting, and people have jobs for decades. And so he has a book called Doorman. What's that? Yeah. Yeah. No, we lived there for a long time. We did live in a doorman building. We go back and high five the guys. It's great. They can be very close knit communities. Anyway, he's done a lot of different things. But this one was about, this study here is from a Midwestern high school, I believe. Is that right? Called Jefferson High School. I should have called it Sunnydale. That would have been good. Buffy fans? I don't know. And the color scheme is what you would get with babies in a hospital. And the idea is over time, over a 6-month period, this is the record of what happened. So of course you look at this and one could say, and there are numbers associated with this. So these are little, in the 63 I think that is. So these are little pairs that were not involved in this questionable looking arrangement up here, which does, so one of the things about this is the dynamics have been taken out of this, right? So you can't, so this is just a accumulated network. So that is a very tempting thing to do because you can make a picture. I mean, what are you going to do, right? At some point, if you take any particular slice, like a day, and this is a problem with looking at any social interaction. So if you look at the interactions between people on Twitter or Facebook or in the real world, and you just take a 10-minute slice or a 1-minute slice or You get different textures to their social connections. So, how do you define a friendship from a remote sensing point of view? It's tricky. Yeah, so this is not really, it's a little, it's fun. You read the whole paper and so on, but that's a little misrepresentative. So this is an unfortunate aspect of, I was not involved with this, but the college I went to, Trinity College in Melbourne Uni, so it's one of these, it's trying to be like Oxford, right, where you have the place and you have the colleges around it. And they're very nice places, beautiful places. But there was a secret group that every year would put up a map once a year, which was this map, basically, for the college. It was just, who kissed whom. But it was called the Snug map, Anyway. And they put it on the big doors to the dining room, which was sort of a Harry Potter situation with, you go to dinner with your gowns on and all this sort of stuff, and there's Latin grace and all that sort of business. And then it was defiled by these idiots. All right, so, okay, so lots of other things you can think about. Friendships, of course, acquaintances. These are, as I was sort of saying before, you have these different levels. Boards and directors. So this is an interesting example of bipartite affiliation graph, of which there are many, right? So there are movies and people. I mentioned Metacritic as an example. So there you have movies, movies and actors, and then you also have the critics, and you have the people evaluating them as well in terms of paying money. You can think of, this is really the best way to start thinking about social phenomena, actually, because there are, and we'll get to this later on when we talk about the small world story, that people come together through context. Like people are in this bottle episode here, it's an unfortunate situation for you. But there are reasons for people accidentally coming together, and there are because you share some affinity. And it can be, of course, work are big things, and local geography, your neighbors just around you sort of have come for some various reason. Sports, religion, these are reasons for people to come together. So lots of models of social phenomena where that's all absent, and they're just trying to sort of make some organic thing that grows. Often fail because they don't have that context structure. Organizations, yes, so again, a place where data can come out of, because organizations will, happily follow what everyone does with their email and so on, and analyze them, which is bad. So we don't get data from these things. We don't get data from these characters. We do get data from this madness. But these are all these are social interaction networks. And it's funny. I've had that line sitting around here because I sort of felt bad about it in maybe 2006. Sort of the proto versions of these slides. I started to put this particular page together, I think. It's just gotten worse, right? It's the NSA and so on. It's bad. All right, so we don't want to do those things. There's a close-up for you. All right. These are now, so we went from physical to interaction kind of ones, which are more fluid and flexible, and then to relational ones where, well, there'll be money and goods exchange, but these are more informational, and they sort of live in a more abstract kind of situation, and some of them may have no actual impact, right? So consumer purchases, these are gigantic databases. And I talked about them before. So something even more abstract would be just networks of words based on their meaning. So what does that have any physical impact? Words do a lot of work. They're very useful characters. But it's pretty abstract at this point. Ideas and databases, knowledge. There's a cost in keeping the Wikipedia, alive and not filled up with madness, right? That is costly to preserve it, I guess. But the ideas sort of exist in abstract. Mathematics, for example. Other ways to kind of create these. So this is just to talk about creating these relational networks. Often metadata is a story, and this is used in this funny way even more recently, right? We're just collecting metadata, like everything. The metadata includes the document. Anyway, so this term gets used as if it's a pretty benign thing, but it can be quite rich. Tagging, which emerged, early 2000, people started to do it in this social way. Funny words like bibsonomy. But became very useful because this is the non-experts doing things. They're saying, okay, this book has these things in it, or this movie has these things in it. People will happily sort of tag things. And it gave you ways to, you could sort of see these word clouds around objects could help you see how they're connected. So rather than using something like ABC, right, that ABCDarian madness that we talked about, which is against God, or using your idea of God to sort things out, you can crowdsource it. All right. So these are incredibly interesting things. This is an example that's just impossible to see, I suppose. That's pretty hard. This is based on scientists clicking around. It's another way of, so again, it's this kind of crowd version, but you get to see, so let's see, I think I can read something. So organic chemistry, physical chemistry, this is statistical physics, I think. So you've got that kind of feel over here, environmental sciences. So you'd have to look at this. So social workers out here. So you can start to see how, knowledge and science, or as it functions, science as it functions now, not necessarily what knowledge really is or should be, how it's structured. And that's a revealed kind of picture. That's cool, yeah. I'm not going to show that, but it is a dog. Well, do we need a psychological break? Let's have a psychological break. Oh, you can watch it on YouTube. All right. Man, it's just a dog and some leaves, really. It's not a big deal. All right, we're just going to...
The question I'm asked most often as a defense attorney is whether I can tell if my clients are innocent or guilty. I don't care.
How to Get Away with Murder premieres tonight after Scandal on ABC.
Good. Thanks for telling us how to get away with murder. Yeah, that's great. Clean our heads. Meanwhile, there's a cat in the window thinking, one day I'll kill all of these people. But the food is good. And it just goes back to sleep. I've been up to something like this for about an hour. All right, so, oh no, gone. All right. Please, come back, go on, go on. Yes! Yes! Fantastic. Fantastic. Good job, buddy.
Are you having fun?
I'm having fun. Yes, we're having fun. All right, so there you go. That's just no, we're right. Okay, we're through it. All right. So look, that was a broad taxonomy of networks. I mean, should be nothing terribly surprising, but I think it's reasonable to think about these things. What's in front of you? All right, so here's a problem with all of this wonderful data and network story, is that they're often a horrible mess, right? So this is tiny. This is a random network, 500 nodes, 1,000 edges, just 1,000 edges. It's nothing, 1,000 edges, which we did this little high-level calculation over here before, right? So it's an average degree of 4, right? So each edge, each link has 2 ends, and so we get 2,000 ends divided by 500 gives us 4. So on average, we have 4 friends, which isn't that much. That shouldn't be that bad, but it is 500. So some of these characters out here have none. They missed out. So it's and we'll get to this later on. These are just being randomly allocated, randomly thrown down, and there are different ways to think about how to do that. But it is what we will call a random network. That's a horrible thing, and it is random, so it shouldn't have much structure. But that is a horrible beast. I have to put in practice quotes. So that is a very graphic analogy which aids understanding wonderfully while being strictly speaking wrong in every possible way, which is not quite what's going on here, but I just want to put it. Ponder Stibbons, excellent, yeah, who's in charge of the high energy magic laboratory. All right, so we have to get out meaning from these things, and everyone wants to make, because it can be fun to put up a network, it can be cool, but I have to say that example for the product space, it's a slice of it. It's a well-crafted rendering of the real network. Because if you did that, it would be a hairball. So a lot of the links have been removed in a certain, using a certain criterion, which is okay, but it's not. You're not actually looking at the real thing because You can't. I guess you could sail around in some, but you can't even do it in 3D space, right? That's the thing. There are, from graph theory, embedding theorems. So given this network or given this object, like what's the minimum dimension that you could stick it in and kind of have everything line up properly? But yeah, and there are clever things for rendering networks that are where you pretend that each link is a little spring and so on, and there's some, you put in some ad hoc force thing and it stretches things out and so on, so you can force it to lay out. But if it's an inherently and these are so networks are high dimensional constructions, and you can, if you like, start to think of the degree, the local degree, as the local dimension, and it does function somewhat like that. So if you think about a one-dimensional object, and we imagine we've got these nodes here, right? Everyone has a degree 2. If you go to 2 dimensions, everyone has a degree 4. And then if we pop in this direction, we have degree 6, 3 dimensions. So we get 2 times the number of dimensions is your degree. So you can kind of think of it like that, right? So if someone has, you have a network where there's some entity has 10,000 friends. Locally, they have a property of a very high dimensional space. Yeah, so it'd be hard to stuff all of those things into 2 dimensions. That's the problem. All right, so I'm going to line these up. I'll talk about some of them, and we'll continue talking about, what's today, Thursday, right? We'll continue talking about them on Tuesday, and then we'll get into models. This is just a list of a number of the most important ones. You know, in time, maybe these things will change, but they've been fairly steady. And so well, I'll tell you about them on the following slides. Degree distribution is just sort of in a different color, but it could be in like, 50-point font. So that's the elephant in the room that's standing on top of you. And you're wondering why it's like hard to breathe. But, so one of those elephants, yeah. So there's more. These are structural. These are all structural things. These start to get into the dynamics of the system, and this sort of lazy extra point here is coevolution of the network structure and processes on the network. They're huge, gigantic pieces, and this is sort of a big open piece that doesn't really have these broken down aspects. Okay, so I'm going to go through and talk about these pieces, and we'll come back to some of them very deeply. So degree distribution will matter for scale-free networks. Clustering matters for small world networks. Network distances matters for small world networks. And in general, all of these, they matter very specifically for those. They matter for most real networks. All of them matter for most real networks. All right, so degree distribution. So I said, we've talked about degree, just how many friends you have. Degree distribution then is, well, you can maybe you take a real network and you look at all the degrees and then you make a histogram, right? Simple thing, make a histogram. Ones with 0 friends, 1 friend, 2 friends, 3 friends, you just make a histogram. So you can do that. You can think of theoretical networks, or you can simulate them and so on. You produce, or you can say, I want it to have this degree distribution. So you can do this too, right? That's okay. And the way to think about this then is whether you've created it or just measured it, it's the probability. You can think of it then as a probability that if you randomly grab a node from this network, it will have degree k. This turns out to be related to, but importantly very different to what happens if you randomly select a friend of yours, right? Or you jump, we talked about links being really important, so you could go to look at the whole network, jump on a random link, which is a different thing to do, a random link. And then flip a coin, choose one way to go down there, and then look at the degree of this person. That's different, right? You get a different result for that, and it's very important. So it turns out your friends are strange and weird, which you already knew, but they're strange in a network sense. And on average, they have more friends than you, which is sort of the worst part. Okay. So that's been known for a while, but it's sort of it seems to be, there are papers even recently in the last year or two saying, well, it's not just that, but they have more citations than you. If we talk about the network of, like you go to Google Scholar and create the network of scientists who are registered there. And if you take any one person and look at their friends are always doing better than them. Which is kind of disappointing, right? So, but it suggests it's sort of built in might be that this kind of keeping up with the Joneses thing is just there, right? that you're always going to be on average worse off than everyone else. Just a little bit, enough to make you want to get better, right? Yeah, that's very interesting. Okay, so, we've got the no degree, we've got this business, and here is, it'll be assignment 6 now, I suppose, but in the distant future, there'll be a question or not, depending on pleading levels. This is a classic. This is a classic, right? So the pure mathematicians just ate this for lunch in the 50s, I think, and 60s. You get a Poisson degree distribution. So if you take n nodes and you have m edges, and then you just randomly choose pairs, and you go point, 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 right? Randomly choosing pairs. If you've already chosen a pair, you just ignore it and you go, randomly choose again. Then you'll get, and if n and m are large enough, you will always get a Poisson degree distribution. So Poisson distributions appear for waiting times and other things. It's a very natural kind of distribution that appears. You don't get a Gaussian, that's important, which you'd think you might, but you get a Poisson degree distribution. So this is, so probably that you have degree k. This is the average degree in here, so you could put either minus z if you want. I know this is a blending of things, either minus z and z to the k over k factorial. So Poissons look like this, right? They have this kind of form. They have a tail. They have a skew, but they don't have heavy-tailed distributions, right? They're not that kind of network. So if you reach into the box that's got n and m marked on it, and rummage around and pull out one of the networks, it will always, and they're large enough numbers, you'll always get a Poisson degree distribution network. And in the real world, you never see this. This is a very odd kind of result. And it's because networks are made, they've been built, there's been some evolution, and they tend to make a very small subset, relative to the whole possible set of networks, a very, very small subset that have these things like skewed distributions and so on. A very, very small subset, which you will never get if you're fishing around in the box. And that it's kind of opposite of what you get with statistical mechanics, which is to say that this configuration of atoms here is indistinguishable from a bazillion others, right? We feel the pressure and temperature and so on that we have in the room. We can move molecules in all sorts of ways and it will feel exactly the same. But the one where they're all in the corner over there is an incredibly low entropy state. It would be bad for us. And it's not findable. They're all equally probable though, right? So each state is equally probable. The exact one we have now is the same probability as the one that's up in the corner. It's just that there are an unbelievable number of microstates that look the same macroscopically. So how it feels, like we can hear some air, I don't care which molecule, you can't tell. So yeah, that's a whole other field, but it's sort of the opposite with networks. The ones that you would get that are the most likely, if you rummage around in the box of networks, you never find the real world because there's a mechanism that's building them. This is a big deal. Okay. Scale-free networks, and we'll get to that in a bit, have these, yes, of course, power law size distributions, which you know all about, right? And the term that popped up there was scale-free for a start, but also hubs, which is the idea that there are some nodes that have many, many friends, whatever it is, or the high degree, and they control or govern the dynamics on the thing. So if you think of disease spreading, it's an appealing story, right? Disease spreading, it hits the big one, and everyone gets it. Or if it's gossip or something like that. Now, functionally, things don't behave necessarily like that at all, right? So you can't just tell Oprah, you can't just go and sneeze on Oprah and give everyone a disease, right? Or tell her your favorite, product that you want to sell. There's a lot of, these people are much stronger and resilient. But sort of in a bare network sort of thing, they're just the very simple models, yes. Yeah, they allow for spreading. So a lot of networks seem to be like this. Of course, it depends how costly the links are. So we had this example before of a link. If we think of the real social network in the world where a link is, I don't know, you would loan the other person some money or something like that, some percentage that's normalized according to your wealth, right? And then you could dial that amount up and down, and that would make a somewhat small network, right? The people who are actually really genuinely close, to something where you see just one person recognizes the other person's face. So Oprah doesn't recognize me, but I can say, hey, Oprah. On a plane. Anyway, yeah. So that will give you a hugely skewed distribution, because suddenly you have nodes in that network that have hundreds of millions of connections, people pointing to them. Okay, but if there's a cost to the link, if Oprah has to, talk to everyone and be buddies with them, and then that's not going to work out. So that's an obvious piece that was kind of added early on once all this story started to pop out. And I was saying that hubs, at least in a simple way, you'd think, oh yeah, they're going to let things spread and all sorts of stuff. But it depends what's spreading, and we'll see examples later on where in fact they very much stop it, right? And kind of in the sense that Oprah is not going to just listen to anyone and then spread it to everyone else. Oprah's still a good example, I think so. All right. So as I've said, these random networks are the Erdős-Renyi, so they're named after a couple of famous characters involved with their work, but lots of people worked on this. So they're a construct, right? They live in mathematicians' heads. That's what they are. Scale-free networks, they're growing ones, and they come from a plausible mechanism, and it's the rich gets richer one in the network version. So we'll look at it. It says slightly different ways of calculating things, which will be fun, but you've been there. It's good. So there's certainly randomness out there as well, though. So it's not to say that they're all like this. There are other kinds of networks. And certainly real networks have a large amount of randomness associated with them, right? And we'll get to exactly how that works. But the big piece is the degree distribution. So something, and I'll repeat this, something that you might want to do is say, okay, here's my real network. It's whatever it is, the disease network, these human diseases are connected through the genes that are involved, something like that. Any network you can think of. So let's take it, let's say, all right, here are the degrees of all of the nodes in the thing. And let's then randomly rewire the whole thing. Let's do that a bazillion times. So we're going to fix the degrees. So if there's something that has 37 friends, it's going to have 37 friends. This one has 73, the most random numbers, between 1 and 100. We're going to preserve them, but we're going to mix and mix and mix. So we can make all these other versions of the network where we've got the same degrees. Right? So you randomly rewire it. And then you take your original one and compare it to these new ones you've made and see beyond the degree distribution, which we're saying is such a big deal, beyond the degree distribution, what else does it have that's non-random? And we'll get to that. So we'll get to that later on. But the degree distribution is the first thing. Okay, so that seems to be primary. All right, I'll tell you about two more things and then we can wind it up. I think, yeah. So these two are similar, sortativity and homophily, right? So this is, so it's the opposite of homophobia, right? It's homophilia. It's the liking of the same. And it's birds of a feather flock together. This has been described in sociology for a long time, and also by just normal humans who understand reality. So there's some sorting that's happened, right? Whatever it is, based on some similarity that the nodes have. So the nodes can have all sorts of properties. And when we're just talking about bare networks, well, the simplest property you can think about, the only property in a very plain network is the degree. That's the only feature a network has. It's how many friends it has. So you can think, so this has been a fruitful thing to think about. Well, what are the correlations like in this network? Right? So again, it could be all sorts of things. With people, it could be age and gender perhaps, and all sorts of things that where there are actually correlations that are not random. So you do the well-connected nodes connect to other well-connected nodes, or is it somewhat opposite? And it turns out that in, there have been some studies, but sociological ones more than that is kind of the case. It's a positive kind of a sortativity. So a sortativity is this word, right? So similar degree nodes connect to each other. And disassortative means that high degree ones connect to low degree ones that also connect to other high degree ones and so on. So these are typically social, at least some studies have suggested this. I guess we could be interested to see this done again with some of the more recent data sets, but boards of directors, co-authors, so this is academia, right? There are lots of data now on that. Actors. And these ones are maybe more technological or biological. So that there's a jumping back and forth. As you move through the network, you're on a high degree node and then you surf over to the next one and it's low, relatively low, so you see a choppiness in the structure. But most structures, whatever they are, correlations is sort of a basic thing to start talking about. Where it's landforms or patterns of activity, if it's earthquakes, whatever it is, what are the correlations like? Financial time series. So you can think so networks, yes, correlations, you want to do that. It's a hard tapestry to think about though. It's a very hard thing to think about. I want to say it's hard to build networks with specific properties. Oh, I should add that here. So it's easy to build certain kinds of random ones, but if you want to say, I want this, property X, property Y, property Z, really hard. So there are some construction property mechanisms we have that will do the things we'll talk about, but you can just say, well, I want a little more, and it turns out to be just terribly difficult. So let me tell you about one more, and then we'll go. So clustering. So your friends tend to know each other. We'll come back to this. Yeah, we'll come back to this on Tuesday. But there have been a couple of measures that have proposed and have stuck. So these have become pretty famous. This is a more graph theoretic one. This was a fairly common sense basic one by Watts and Strogatz in the Small World paper. It looks a little funny, but the idea is, so here's the center of this little network here, right? So there's more network going away, but you talk about the ego being the center in this little piece. So they have all these friends, they have these 5 friends, and then the issue is how social is this network? How well do their friends, to what degree do their friends know each other? And so this is a simple calculation. If you have k friends, then you have k choose 2 possible friendships around you. Or k times k minus 1 over 2, that's what that is. So it's the binomial k choose 2. And then this little bit, that's from the adjacency matrix, it's capital A, so AJ1, J2 just says, let's look at the neighborhood around, right? This is the neighborhood. And if there's a friendship between them, so if this is J1 and J2, if there's a friendship between them, this will be a 1, it'll be a 0 otherwise. So you're simply using this little structure here to count up the number of friends around, number of friendships around a node in its local neighborhood, divided by the number of possible friendships, right? So if it's completely asocial, none of your friends know each other, then this is a 0 on top, so you get 0 clustering. If everyone knows everyone, you'll get a 1 on top. And then this thing here is saying, well, let's compute it locally and then average it across all nodes. That tends to, well, I'll say this again, but this tends to discount really well-connected ones. This is a global average of a local quantity. This is an average of 2 global quantities. So we'll explain this properly on Tuesday, but this is the number of triangles, right? So the number of triangles in the network, it's more graph theoretic, divided by, there's a 3 for a certain reason, but divided by the number of so-called triples, which is just, there's a friend here, and a friend here, A, B, and C. So basically you're figuring out what's the probability that if you have you're estimating the probability that given this structure in a network, you find that there's an A, B, and C connected like this. What's the probability that these 2 know each other? So that's a very intuitive thing to ask for. So this one's used probably a little more, but these prove incredibly fruitful pieces. Fruitful, why do I say it? Okay, so good. So we're going to sail on with these aspects of networks on Tuesday, and then we'll get into these models, which is really good, great history of science madness as well. So we're going to take it easy. It's going to be okay. Okay. Yes. So Tuesday, right? All right, Tuesday. I'll update that for you.